Some structures, some molecules have more than one valid Lewis structure. Let's look at ozone, O3. So I didn't leave myself a lot of room, but I'm going to draw the Lewis structure for ozone. So I have 3 oxygen atoms. Each has 6 valence electrons, so I've got 18 valence electrons. I can make 18 dots. So there's 2, 4, 6, 8, 10, 12, 14, 16, 18. Close, but not quite. So I'm going to connect those because those are the bonds. We're short a pair of electrons, so we need to do some more sharing. I'm going to take one of the pairs from this center oxygen, and I'm going to move it over here and share it. Now, does each of those oxygen atoms have an octet? Yes. So, good. This is not completely symmetrical, is it? We've got O, 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 but we've got a double bond on one side and a single bond on the other side. Why isn't the double bond over here? Could we draw a Lewis structure with a double bond to the other oxygen? Well, sure we could. Is there anything better about one or the other? These oxygen atoms are the same. Why does one get a double bond and this one get a single bond? Why not this? Well, these are 2 equally valid Lewis structures. So we're like, well, what's going on there? If we look at ozone and study it, what we find is that the bonds between the center oxygen and this one and the center oxygen and the other one are actually the same in length. We can measure that, the bond length. One isn't longer than the other. And so it actually exists between these two. It's not either one. It's between them. Lewis theory doesn't have a good way of drawing something like that. Lewis theory is the simplest method of understanding these things, and it doesn't take care of everything, and this is one of the things that Lewis theory falls short on. So the way we represent this is we put a double-headed arrow between the 2 structures, and that indicates that these are resonance structures. The word resonance suggests to me of a vibration back and forth, right? But that's not what's going on. The molecule is actually a combination, an average, a hybrid of those 2. The difference generally between resonance structures is the placement of a double bond. Moving a double bond from one atom to another, and those atoms are the same. That's usually what happens. So the actual structure is called a resonance hybrid. Just like if you had 2 dogs, a German Shepherd and a Golden Retriever, and they had a puppy. The puppy would have some characteristics of both parents, but it would really look like neither, right? And this puppy would not look like a German Shepherd on some days and like a Golden Retriever on other days, right? It's always a combination of the 2. My children are nice resonance structures of my husband and myself. So what we actually have with ozone is the real ozone is between the 2 resonance structures. It's a combination, and so really these bonds are more like a 1.5 bond. Not a single and a double, but more like a 1.5. In the Lewis model, electrons are localized. We have to put them on one atom or another. We can't show them being spread out over the whole molecule. But In actuality, the electrons are often delocalized over several atoms or bonds, and that's called resonance stabilization. It lowers the energy of the molecule. And the other theories that we're going to look at can explain that better than the Lewis theory can. So let's write Lewis structure for NO2 minus, the nitrite ion, and include resonance structures. So there's a big clue that there's going to be at least 2 resonance structures. Well, connecting these, we've got nitrogen and oxygen, and we look at the periodic table to see which is more electronegative. The oxygen is. So oxygen is most likely going to be on the outside, and the nitrogen is most likely going to be the central atom. So I'm going to put the nitrogen in the middle, and I'm going to put the oxygens next to it. Then we have to add up valence electrons, so the nitrogen has 5. 2 oxygens, each oxygen has 6 valence electrons. And then we add 1 for the negative charge. So that gives us 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. So I have a single bond here, a single bond here, but I'm short electrons. I need a double bond. So I'm going to take one of these lone pairs and give it to this oxygen because she's missing some electrons. So now all of my atoms have 8 valence electrons. To finish this, I need to put brackets around it and a negative sign. What tells us there's a resonance structure is here I have a double bond between nitrogen and oxygen. Here I have a single bond between nitrogen and oxygen. And so I can move the double bond. It's still between the same 2 atoms. It's just who gets it. That's what tells me there's resonance. So I'm going to draw that over here. I don't need to go through that whole long process again. I'm just going to draw it differently with the double bond to the other oxygen. So that's got a lone pair. Now this oxygen over here has the 3 lone pairs, and this one has the 2 lone pairs. And brackets and a negative sign because it's an ion. I'm not doing this on purpose, but you'll see that here I put the lone pair under the nitrogen. Here it's on top. That really doesn't matter. It does matter that this oxygen has 3 lone pairs, and over here it had 2, because here it had the double bond and here it doesn't. They need to have octets. So those are the 2 resonance structures for the nitrite ion. Any questions? Well, we've done molecules in polyatomic ions that are fairly straightforward. Sometimes it gets a little messy. There's several different structures that you could draw, and we know that they can't all be correct. So we need something else to help us decide, and that is formal charge. This is a fictitious charge that's assigned to each atom. It's somewhat analogous to oxidation state in that it's not an actual charge, it's something we made up to help us figure out what's going on. And we ignore electronegativity when we do this. We're looking at the Lewis structure that we have drawn, and the formal charge is the charge it would have if all the bonding electrons were shared equally between the bonded atoms. So that's one way to look at it. Another way is to look at it as the difference between the number of valence electrons that an atom has and the number of electrons that it owns in the Lewis structure. So this is the way your book talks about it. The formal charge equals the number of valence electrons minus the quantity, the number of non-bonding electrons on that atom, plus half of the bonding electrons that that atom has. If that works for you, you go right ahead and do it. I'm going to show you a little bit of a different way of thinking about it. It's going to get us the same answer. I just think it's less confusing. Formal charge rules. The sum of all formal charges in a neutral molecule must be 0. The sum of all formal charges in an ion has to be equal to the charge on the ion. Small or 0 formal charges are better than large ones. And when formal charge cannot be avoided, the negative formal charge should reside on the most electronegative atom. So what we're going to do is we're going to draw a Lewis structure, and we're going to look at the formal charges on each atom. These rules tell us, am I doing a good job with this Lewis structure, or do I need to adjust it? We're trying to make the Lewis structure with the lowest formal charges possible. Many times you can get 0 formal charge on all the atoms. Sometimes you can't. And so this bottom guideline says that if you have a negative formal charge, put it on the more electronegative atom. This is what helps us decide between different Lewis structures. So let's look at hydrogen cyanide. Now this table is a little bit hard to look at, I think. So I left myself some space, and I'm gonna kind of walk you through it. So here is the Lewis structure for cyanide. Here's one, and here's another one. And so we're going to compare these two. So I'm going to draw them down here. So first we have carbon being the central atom, and a lone pair on the nitrogen. Our other option is nitrogen being the central atom and a lone pair on the carbon. Now, I have talked about a couple of guidelines that would help us choose between these. One is that the more electronegative atom is generally terminal, and so that suggests that this is the better Lewis structure. I also talked about the number of bonds that atoms like to make. Carbon likes to make 4, nitrogen likes to make 3. And so that happens here, does not happen here. So both of those kind of rules of thumb tell us this is more likely to be correct. But formal charges can also help us. And we'll do it on this simple atom molecule. Sometimes those other guidelines don't work on more complicated ones. Okay, so here's how I think of formal charges. What I'm going to do is I'm going to divide each of these bonds in half. And remember that each bond is 2 electrons, right? So what I'm going to do is I'm going to look at the electrons that hydrogen owns. It owns half the bond. So hydrogen has 1 electron. Here, carbon has 1, 2, 3, 4 electrons. And the nitrogen has 5. Do you see that? That's the number of electrons it owns. And we're going to compare that to the number of valence electrons that atom has by itself. So we're going to take valence electrons. Hydrogen has 1 valence electron, not that, 1 valence electron. And in this structure, it owns 1. So I'm going to subtract that, and I'm going to get a 0 formal charge. Carbon has 4 valence electrons. I'm going to subtract what it owns, which is 4, and that's 0. Nitrogen has 5 valence electrons, and in this structure it owns 5, and so that's 0. You're like, well, that's some fancy math. Yeah, it doesn't really make a lot of sense, does it? This is my way of thinking of what they're doing up there. If you like that, you'll understand it. I'm not going to explain it. So over here on this other structure, I'm going to do the same thing. I'm going to cut each of these bonds in half and then look at what's going on. So hydrogen has 1 valence electron, nitrogen has 5, carbon has 4. We're getting that off the periodic table. Then I'm subtracting what each of these atoms feels like they own in this particular Lewis structure. So the hydrogen owns 1. How many electrons, oops, that's not what I wanted to do. How many electrons does the nitrogen own in this structure? 4. 1, 2, 3, 4. So minus 4. So that gets me plus 1. And how many does the carbon own? 5. So 4 minus 5 is negative 1. Comparing these two Lewis structures, we're going to compare the overall formal charges. This one has all zeros, so that's going to be good. That's going to be the better one. This one has a plus 1 and a minus 1, which isn't necessarily a big problem, but the negative one should be on the more electronegative atom. Nitrogen's more electronegative. So this is just not good. That's not good. And so that tells us that this is the preferred Lewis structure. Any questions? So let's assign formal charges to each atom in the 3 resonance forms of N2O. And they're telling us that nitrogen is central. So that's not what we would necessarily expect here, but nitrogen is central. Which resonance form is likely to contribute most to the correct structure of N2O? Okay, so nitrogen's, well, let's see. Let's go back to our regular colors. Nitrogen, nitrogen, oxygen. So we've got 2 times 5 for the 2 nitrogens. We've got 6 for the oxygen, so we've got 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. Yes?
You can have 3 resonance structures if nitrogen is central.
We'll figure that out. It's a good question. So obviously we need multiple bonds here, right? Because we have 2 atoms that are not happy. So let's take one of these from the nitrogen in the middle and make that into a bond, maybe with this oxygen over here. Like, okay, well, getting better here. Now the middle nitrogen and the oxygen are happy, but this nitrogen over here isn't happy, so we could take this electron pair and move it over. And now we've got octets on everybody, right? So now to draw the other resonance structures, we're going to see, well, what could we do just by, shuffling some double bonds around? Well, you might say, well, there's a double bond on each side. What is there to move around? Well, could we also draw this with a single bond and a triple bond? Could that work? Yeah, it could. So nitrogen, let's do a triple bond here and a single bond with the oxygen. So I've got 2, 4, 6, 8, 10, 12, 14, 16. That could work. Where else could I put the triple bond? With the oxygen, right? So I could put the triple bond on the other side, triple bond with the oxygen instead. And so these are the 3 formal charges, not 3 Lewis. Start over. These are the 3 resonance forms. You're like, okay, that's kind of sketchy looking. One of these is going to be better than the others. And the way to tell is by looking at formal charges. So I'll get out my orange marker, and we're going to pretend that we're cutting, oh good grief, stop doing that, cutting the bonds. And then we're going to look at the difference between valence electrons and electrons owned in the structure. So I'm not going to do the subtraction. Nitrogen has 5 valence electrons. How many does it own right here? 6, right? So 5 minus 6, this has a -1. That's its formal charge. You see what I'm doing there? Once you see it, it's not hard at all. The nitrogen, again, has 5 valence electrons. How many does it own right here? 4, right? So 5 minus 4 is +1. Oxygen has 6 valence electrons. How many does it own? 6. 6 minus 6 is 0. So those are the formal charges there on that one. Let's look at this next one. Nitrogen has 5 valence electrons. In this structure, it owns 5. 5 minus 0, 5 minus 5 is 0. Here, this nitrogen is owning 1, 2, 3, 4. 5 minus 4 is 1. Oxygen has 6, and here it owns 7. 6 minus 7 is -1. Everybody okay with that? What's the formal charge on this nitrogen on the left? +2 or -2? -2. It came with 5. Here it owns 7. 5 minus 7 is -2. How about the nitrogen in the middle? +1. And the oxygen? Oxygen has 6 valence electrons. Here it owns 5, right? So this is +1. The thing the rules we're talking about with all the formal charges adding up to 0 for a neutral molecule is kind of a check on whether you did it correctly. -1, +1, and 0 add up to 0. These 3 numbers add to 0. These 3 numbers add to 0. If it's an ion, they will add to the charge. So we are going for lowest formal charges. So that tells us this is not the most important one, because here we have a -2 and a 1 and a 1. And these are 1s and 0s, so these both have lower numbers. We choose between these two because we want the more electronegative atom to have the negative charge. Remember, an electronegative atom is more attractive to the electrons. Well, looking at the periodic table, we see oxygen is closer to fluorine. Oxygen is more electronegative. Here, oxygen has a formal charge of 0. Here it has the -1. And so this is going to be the most important resonance structure for that molecule. It will contribute the most to the correct structure. The correct structure is still a combination of these, most likely, but it's going to be closer to this one than to the other two. Any questions? Draw the Lewis structure, including resonance structures, for diazomethane. CH2N2. Carbon is central. Then assign formal charges. Okay, so if we put carbon as the central atom, we got 2 hydrogens. Those have to be attached to the carbon. And then we've got 2 nitrogens. We're going to attach both of those to the central atom. Now you might ask, well, why not, string them along and put the other nitrogen out there? Well, nitrogens don't do that. Carbons will tend to form chains like that, but nitrogens usually do not. What's the total number of valence electrons for this structure? 16. 1 and 1 is 2, plus 4 is 6, plus 5, 16. Oops, that's not what I wanted to do either. So 2, 4, 6, 8, 10, 12, 14, 16. Well, is that going to work? Is it 18? Carbon has 4. Each hydrogen has, yeah, it is 16. Is that going to work? Can we make double bonds there? That is not going to work. What could we do to make it work? We're going to have to change our skeleton. The nitrogens are not going to be next to each other, but what if one of these hydrogens was coming off of a nitrogen? Let's try that. So I'm going to take this hydrogen with its bond and move it over here. So we don't have to do any counting or figuring or anything. Because the other way, it was impossible to have octets for everybody. So that just was not going to work. Now we have a possibility for a double bond with the carbon. We could take this lone pair from nitrogen and bring it over here and give carbon an octet that way. So carbon's happy, the hydrogens are always happy. Nitrogen's happy, one of them is. What about the other nitrogen? What about this guy? Is he happy? No, not happy. We're going to have to move the other hydrogen. Okay, so this is one of those molecules that is just not real straightforward. So if I move this hydrogen and attach it down here on the nitrogen, okay, we're getting closer. We're going to have to make another double bond though, right? So I'll take this lone pair here and make a double bond up there. Does everybody have an octet? Yeah. Like, ooh, that's a mess. Yeah, it is a mess. Now, it's telling us that there's resonance structures. This is like the last one where we could we have 2 double bonds. We could break that into a single bond and a triple bond. So I'll draw them over here a little more nicely. H, there's the nitrogen. We could put a triple bond here to the carbon and then a single bond to that one. Or we could put the triple bond to the other nitrogen. And so these two are more easily recognized as resonance structures because here we've got a triple on one side, here we've got a triple on the other side. But this is also a resonance structure where you split the triple and you have a double on each side. Question?
Why do you draw that one bent and those two straight?
That's a good question. Why did I draw this one bent and those straight? Because of how I started off with this one. That's the only reason. Because I started off with the hydrogens up here. So it actually would look much nicer, and I'll just redraw it because it'll make everything else easier. H, N, double bond with the C, double bond with the nitrogen, hydrogen. And then we need lone pairs. Yes?
Is there a reason why they specify a guide in the central?
Yes, because they don't want you putting, they want to let you know that it's not an option to put the nitrogen here and a carbon here. And so they're trying to give you a head start instead of letting you puzzle out the whole messy thing. Because if you had all the different combinations available to you, then it would get, it would just take longer. Okay, so everybody okay with these resonance structures? So these are resonant. And then we need to look at formal charges. So I'm going to cut all the bonds in half. This is like they're getting divorced and they're just splitting everything equally. You get half, I get half. Now, honestly, with the hydrogens, they always end up with a formal charge of 0. So now the question is saying assign formal charges to all atoms that have formal charge. So it's telling us we could ignore zeros. So we're going to ignore all the hydrogens because they're just going to have zeros anyway. Well, let's look at this nitrogen. In this structure, it owns 1, 2, 3, 4, 5. It came in with 5. So 5 minus 5 is 0. It has a formal charge of 0. This carbon has a formal valence electrons of 4, and it owns 4 here. So its formal charge is 0. This nitrogen is in the same situation as that one. Its formal charge is also 0. So just from that says, well, this is probably a good Lewis structure. We got zeros for everything. But we need to look at everything else. What's the formal charge on this nitrogen atom? 0. You're like, wow, this is getting boring. What's the formal charge on this carbon? Wait, that's not 0. It's 1, sorry. What's the formal charge on the carbon? 0. How about this nitrogen? -1. 5 valence electrons minus 6 in the structure is -1. And down here, what about this nitrogen? -1. And the carbon? 0. And the other nitrogen? 1. So the question doesn't ask us to choose which structure contributes more. But we can answer that. It would be this one because this has the 0 formal charges. Any questions?